DC motors are frequently used where electrical power comes from batteries. The electric motors that power mobile equipment, engine starting motors, and the motors in cordless hand tools, for example, all are battery-powered DC motors. DC motors also have an advantage when high starting torque and accurate speed control are necessary, as in hoist and machine tools. Modern solid-state devices allow AC power line voltage to be rectified to DC simply and cheaply, so DC motors can be used almost anywhere. We saw in Lesson 1 that any motor shaft turns and exerts torque because the rotor poles are attracted and repelled by the stator poles. In a DC motor, the stator is referred to as the field. The field poles are produced either by permanent magnets or, more often, by current in windings on the pole shoes. Most DC motors also have interpoles to help keep the magnetic forces properly aligned under all operating conditions. The rotor in a DC motor is called an armature. Its poles are produced by current in windings which are installed in slots in the armature core. The commutator is part of the armature assembly. It consists of copper bars, usually insulated from each other by thin strips of mica. The armature windings are connected to each other at the commutator bars. Brushes riding on the commutator conduct current to the armature windings. A brush is actually a solid block of carbon held in place by a brush holder and a spring which presses the brush into firm contact with the commutator. Usually there is a short wire lead or pigtail attached to the brush to bring current to it, although in some small DC motors the spring acts as the lead. Now, the simple demonstration we saw in Lesson 1 had one magnet as the armature and one set of armature poles. As the armature turned, its poles were reversed each half turn. An actual motor has many armature windings, each of which produces its own set of poles. The windings are wired together in groups so that like poles combine to produce as many armature poles as field poles. Although the armature turns, these armature poles actually remain almost stationary in the best position to produce maximum torque. Let's see how this happens in a simple two-pole motor with only 6 armature windings. With the armature in this position, current flows in the top brush, divides between the coils on each side of the armature, and is carried out through the bottom brush. It produces poles on the windings like this. On each side of the armature, the individual poles combine, and the coils work together like a big electromagnet with a north pole and a south pole. So the top of the armature becomes the armature north pole, and the bottom the south pole. Now watch what happens to an individual coil as its commutator bars pass under a brush and its poles are switched. In this position, current is flowing in this direction through coil 6, and its north pole is here on this end of the coil. As the armature turns, the armature north pole turns with it until the brush contacts the next commutator segment, shorting out coil 6 so that no current flows in it. The armature north pole jumps back because current coming in the top brush now divides between coils 1 and 5. The armature pole turns with the armature until the next commutator bar slides past the brush. Current now flows in coil 6 again, but instead of flowing in this direction, as it did on the other side of the brush, it now flows in this direction. Its north pole is now on the other end of the coil, and it contributes to the armature north pole just as coil 1 did. Because of the commutator's switching action, the armature poles keep going forward and backing up as each coil is first shorted out and then current is sent through it in the opposite direction. Since the steps are actually quite small, the armature poles stay practically stationary between the field poles. so motor torque is smooth and continuous. Basically, that's how all DC motors work. But there are four main types of DC motors: series, shunt, compound, and permanent magnet. Their operating characteristics, how much torque and horsepower they will produce at different speeds, and how much current they draw, suit them for particular kinds of applications. To understand why they behave differently, we need to look more closely at the relationship between torque, current, and speed in a DC motor. We saw in Lesson 1 that the torque a motor exerts depends on the strength of its magnetic fields, and they, in turn, depend on the current through the motor's coils. The higher the current in the coils, the higher the torque. Now let's see why, in a DC motor, both the current and the torque decrease as the motor speeds up and increase when it slows down. The relationship between current, torque, and speed is easiest to explain in terms of counter EMF. Counter EMF is a back voltage that is generated in the armature coils whenever the armature is turning in the magnetic field produced by the field magnets. If you remember your basic electricity, you know that a voltage is induced in any coil which moves so as to cut flux lines. So when the armature turns, voltage is induced in its coils. The individual voltages add up to a counter EMF. It opposes or subtracts from the applied voltage. Now, according to Ohm's law, current equals voltage divided by resistance. The resistance is the resistance of the coils, the brushes, the commutator, and anything the current flows through. But the effective voltage pushing current through the armature equals the applied or source voltage less the counter EMF. So the current through the armature of a DC motor will be the applied voltage minus the counter EMF, divided by the armature resistance. Now here's the important point. The counter EMF is not constant. It varies according to armature speed. At startup, before the armature starts to turn, there is no counter EMF because the armature coils are not cutting the field flux lines. Full source voltage pushes current through the armature, so armature current is very high. As armature speed increases, however, counter EMF increases and reduces the effective voltage on the armature. Current to the armature decreases. So the faster the armature turns, the less current the motor will draw. Motor speed and current are also influenced by the strength of the field magnets. If we decrease the current in the field coils, the armature coils will cut fewer flux lines, and the counter EMF induced will decrease. The reverse is also true. If we increase field coil current, the counter EMF will increase. These basic principles of DC motor operation are important for understanding the four types of DC motors. Because each type is wired differently, the current, torque, and speed characteristics of each are quite different. In a series motor, the armature and field coils are connected in series, and the same current goes through both. Let's see what effect counter EMF has on motor characteristics. As in all DC motors, there is no counter EMF at startup, and current through the armature is high. The same high current also flows in the field coils. As the armature starts to turn, counter EMF builds up and reduces current in the armature. But since the field is wired in series with the armature, the current in the field coils is also reduced. Both of these effects reduce torque. So the torque exerted by a series motor drops off rapidly at first, though the curve flattens out at normal operating speeds. Even though the torque drops off quickly, series motors produce exceptionally high torques at startup and slow speeds. In fact, they are used when high startup torque is required. Since counter EMF will limit field current when the motor is up to speed, the field coils can be wound with heavy, low-resistance wire, just like the armature. As a result, the total resistance of the armature coils and the field coils in series is quite low. At startup and low speed, before counter EMF is built up, current in both the field and the armature is very high and produces high motor torque. A real disadvantage of a series motor is that it does not have a stable no-load speed. When any motor is relieved of its load, it tends to speed up. In non-series motors, this tendency is opposed by the quickly increasing counter EMF and the resulting drop in motor current. Counter EMF also increases in series DC motors, decreasing the motor current. But because the field is in series with the armature, the decreasing current in the field tends to oppose the increasing EMF. As a result, the net motor current does not drop off quickly enough to slow the motor, and the motor continues to accelerate. Any motor, if it spins too fast, will be destroyed from centrifugal forces in it. The armature will literally fly apart or explode. Small series motors usually have enough brush and bearing friction to prevent this, but large series motors, like the drive motor in a forklift, must be connected to the load directly through gears. No clutches are used. Belts are also not used with series motors. They might break or come off and allow the motor to overspeed. In a shunt-connected motor, the field coils are connected across the line, rather than in series with the armature. As a result, the current in them is not affected by counter EMF. So field current is independent of motor speed and provides a nearly constant field flux. Since counter EMF does not limit field coil current, the coils need to have considerable resistance. They are wound with many turns of fine wire. Because the fine wire carries a constant and fairly low current, the startup torque of a shunt motor is much less than that of a series motor. But because field current stays constant as motor speed builds up, torque does not drop off as fast as in a series motor. Another advantage of a shunt motor is that once it reaches normal operating speed, it has good speed regulation. This means it does not change speed very much as the load changes. This particular motor, for example, produces rated torque at 2,500 RPM. If the load is doubled so that it must produce twice as much torque, it will only slow down to 2,300 RPM. A typical series wound motor would slow down much more under the same conditions. Shunt motors also have a fixed upper or no load speed. They will not run away because the field stays constant as armature speed increases. Large industrial DC motors are often compound wound. This means that they have both series and shunt coils wound on the same field cores. Each set of coils contributes to the field flux. Compound motors usually combine some of the best characteristics of both shunt and series motors. Their starting torque is higher than a shunt motor, yet their speed regulation is almost as good as a shunt motor, and they have a stable no-load speed. There are several different ways of interconnecting the series and shunt coils in a compound motor. Each produces slightly different motor operating characteristics. The degree of compounding, that is, the proportion of the total field strength that is supplied by the shunt and series coils, also affects how the motor will behave. Permanent magnet motors do not have field windings. Permanent magnets supply a constant magnetic field. The field magnets and the armature windings are usually proportioned so that the torque curve is nearly a straight line from low speed through no load speed. A torque curve like this means that the motor produces almost constant horsepower, whatever its speed. Many machine tools and reel winders work best with this type of torque curve. Now, as we mentioned in the beginning, one of the major advantages of DC motors is accurate and relatively easy speed and torque control. To understand how a DC motor's speed and torque can be changed, let's look at a motor running at a constant speed. The motor is producing just enough torque to turn the load at that speed. Motor torque and load torque are the same or balanced against each other. The counter EMF is also balanced against the supply voltage at a constant level. The effective voltage produces just enough current so that the motor produces the torque it needs to turn the load. What would happen if we upset the balance in some way? Suppose we decrease the voltage on the armature. The effective armature voltage drops. Armature current and motor torque also decrease. The motor is no longer producing enough torque to drive the load, and the shaft slows down. This decreases the counter EMF. As a result, effective voltage increases, and armature current increases until the motor is producing enough torque to drive the load at the reduced speed. The situation is stable again, but the motor is going slower. Now, what happens if we adjust the field voltage? Suppose we reduce it. The current through the field coils will decrease, reducing the strength of the magnetic field. Since the armature coils are cutting fewer flux lines, counter EMF will drop. More current will flow in the armature, and the motor will speed up until counter EMF rises again and the motor is producing just enough torque to drive the load at the higher speed. This is how a DC motor controller works. It either changes the voltage to the armature or to the field. Increasing armature voltage or decreasing field voltage will speed the motor up. To slow it down, a motor controller decreases armature voltage or increases voltage to the field. The first job of most DC motor controllers is to start the motor up. Most DC motors larger than 1 or 2 horsepower must be started at a reduced voltage because, as we saw, the motor's resistance is very low. If full power line voltage was suddenly switched on, the inrush current would be more than the source could supply, so controllers provide a voltage which is increased smoothly or in steps as motor speed builds up. Some DC motor controllers also allow the motor to be used as a brake. Actually, even without a controller, most DC motors will limit the speed of a load that tries to turn faster than the motor's no-load speed. A load like this is called an overhauling or runaway load. What happens when a load runs away is that the counter EMF induced in the armature rises above the supply voltage. So instead of drawing current from the source, the motor becomes a generator and pushes current back toward the source. When the current reverses, the armature poles reverse and torque reverses. Even though the shaft is still turning in the same direction, the magnetic forces in the motor are trying to turn it in the opposite direction. So the torque of the motor works against the runaway load, limiting its speed. Now, if we disconnect the source voltage from the armature, the braking effect of the motor will be intensified. The counter EMF is no longer being opposed, so the reverse current in the armature increases, and the braking torque becomes much stronger. In order for this to work, current must have a complete circuit through the armature coils. So when the brake switch is thrown, the motor controller connects resistors across the armature terminals at the same time as it switches the source voltage off. Since the counter EMF decreases as armature speed drops, current and braking torque will decrease as the motor slows down. At zero speed, there will be no braking, so the shaft will not be held stopped. Mechanical brakes are often engaged when the motor reaches a slow speed to complete the braking. Reversing a DC motor is very simple. Reverse the current in either the field coils or the armature coils. When the magnetic poles reverse, the torque of the motor reverses. In practice, DC motors are nearly always reversed by reversing the armature current. One of the reasons for this has to do with a part of the motor we haven't looked at yet, the interpoles, or commutating windings. These are poles installed between the main field poles and wound with heavy wire in series with the armature. Most shunt, compound, and permanent magnet motors larger than about half horsepower have them. Their purpose is to keep the brushes from sparking under different load conditions. But the interpoles can only do this if their polarity is right for the direction the motor is turning. When the motor direction changes, their polarity must also change. Since the interpoles are wired in series with the armature coils, reversing the field connections would reverse the motor, but not the interpoles, and the brushes would spark badly. When you are connecting a motor for reverse operation, remember to swap the armature leads, not the field. Now, we've seen the main parts of a DC motor. We know what they do and how they are interconnected in the four main motor types. If you keep in mind the basic points about how the brushes and commutator work to switch current in the armature coils and how counter EMF affects motor speed and torque characteristics, you will be able to understand why a DC motor behaves as it does. Later programs in this series will deal with motor specifications, installation, maintenance, and troubleshooting.